Good afternoon. My name is Bill Hamill. I'm from the University of Tennessee, and I'll be chairing this session this afternoon. This particular one is surgical robotics, and the latter part of it, teleoperation and telerobotics. So, what what better person to open us up with a keynote than Blake Hannaford? Blake's a professor at the University of Washington, and he's been working in design and control issues in teleoperator systems for a long time, and in recent years has mapped that onto problems in medical robotics, including the Raven experimental test bed that's so popular these days. So welcome, join me in welcoming Blake to give us our keynote introduction. Blake?
Thanks very much, Bill. Thank you all for coming, and thanks to the committee for inviting me. You're going to notice sort of a discrepancy between the summary slide on your right and the actual talk I give in the center, and that's partly because I think some of that is covered. First of all, that is a little more focused and preliminary work, and also some of it's been covered or will be covered in individual talks. So I sort of subtly changed the emphasis of this talk to be on interfaces for collaboration and collaborative research. And what I'm really getting at by that is that where a major part of our energy in the last couple of years has been, rather than developing our surgical robot platform by ourselves, we've been working on disseminating it and creating it as a common platform for a community. And so I'm going to try to just illustrate that and make it a little bit concrete in this talk. That was a click that didn't go anywhere. Okay, so just some admin. You're going to see this Raven that we talk about, and it's now a commercial product licensed out from the university. Many of you have come by our booth downstairs, and I just want to be upfront that that's a company I'm involved in. And also give a lot of acknowledgement to the agencies that funded this work, starting with the Department of Defense peer-reviewed medical research program in the early 2000s, with whom we developed our very first Raven prototype, and then NSF and their computational research infrastructure program generously funded us to disseminate the Raven to 5 other labs in North America. And then some of the specific collaborations you're going to see today were funded by the Qatar National Research Foundation in conjunction with investigators there. So in that first NSF project, we worked with great teams at Harvard and Johns Hopkins and Nebraska, UCLA, Berkeley. And by the way, this work is really keyly, in a very profound way, joint with Professor Jacob Rosen, who is currently at UC Santa Cruz and I guess moving to UCLA. So from one Raven site to another. And then we built further robots for, these transitions take longer than I expected. Okay, but they do happen, so that's good. So we had added additional sites in 2013, and each of these are places that are performing research with our robot. Officially what we call it is a surgical robotics research platform rather than a surgical robot. There's a tremendous amount of hard and valuable engineering that goes into making a device suitable for human use in the operating room, such as Intuitive Surgical's Da Vinci, and we haven't done that yet. So this is only for research and not humans. But we can go up to animal research. And we just have, through our company and commercialization efforts, we have 2 more sites now, and we'll soon be having another site announced shortly. So what were our goals in that original expansion project? So the point was to set up a network of open research telerobots for medical applications. That is, building 7 robots and adding them to the 1 or 2 that we already had. And the idea, of course, is not just to plunk these down in isolation, but to enable collaborations. And to do that, you want to open the interfaces and at multiple levels so that modules can be plugged across between cooperating sites and from outside sites as well. And I'll explain a little bit about those levels. Okay, so first of all, the first level is a physical one, and the tool interface by which surgical instruments are snapped onto the Raven and interchangeable is something that's an open, an available CAD file. So that means that as a researcher, you can decide to work on, for example, a surgical instrument prototype, and then maybe you get a Raven later to embed it into the surgical operations context, surgical robotics context, or you might just work with some other site that has a Raven and arrange to have some tests at another site. I'm also going to give an example about gravity compensation as a sort of way to add a software interface before okay, they switches back faster. And how the software is integrated with ROS, the robotics operating system, which allows us to compartmentalize and define documented and flexible software interfaces within the system, and B, it further expands the possibilities to collaborate outside the existing world of surgical robotics, because so many researchers out there are using ROS. And so, say a motion planner that was developed by somebody way outside the surgical robotics community could be grafted in to perhaps tested in a surgical robotics context. So the open tool interface is specifically the CAD and drawings for the mechanical interface itself, the tool base. Also, we have, through our colleagues in Nebraska, one of the things they contributed to the consortium was an adapter that snaps on and allows old expired instruments from the Da Vinci surgical robot to be used and driven by the Raven. So if you see our configuration downstairs in the exhibit booth, you'll see Da Vinci instruments snapped on. And our partners at Qatar University and SKKU are designing very interesting instruments through that interface. An open source blob of software is not necessarily very useful unless you have the way to, well, before I get to that, here are the types of detailed engineering drawings that we supply you so that you can make a compatible instrument. And the Da Vinci adapter that is working downstairs. So one of the projects is with Qatar University and Professor Jong Woon, who is out there in mechanical engineering, and this is a flexible steerable endoscope tool. Oh, I'm so sorry. Okay, airplane mode. And that is designed to steer a flexible, tiny scanning fiber endoscope, which is a very innovative development from Jong's research advisor, Dr. Eric Seibel. So that allows steering, looking around corners, and providing visualization that's more flexible and steerable than the standard surgical endoscope. So in the last 2 summers, we've, well, actually 2 summers ago and 3 summers ago, we evaluated it in our lab in some teleoperation experiments. The next one is, a lot of people ask us about force feedback and haptics with this system, and if you've read about that field, I've worked on it for a long time, and you appreciate some of the systems engineering and control theoretic challenges of putting a true haptic feedback loop around a surgical robot system. And we feel, one of the very standard approaches that has been tried is developing force sensing for the surgical instruments. And it's very possible to do that, but a supreme challenge there is developing a force sensor that is both small enough and low enough cost and also capable of sterilization. So medical instruments needing to be sterilized, and the two sterilization techniques that are essentially the only two in practical use are the autoclave, which is high pressure steam, and gas sterilization, which is some very toxic gas chemicals. And of course that solves the temperature and pressure issue for the most part, but there's a lot of materials that are actually corroded by those chemical gases, and so gas sterilization is also very harsh. And nobody's developed really a practical force sensor yet that survives this really tough sterilization challenge. But Dr. Choi at SKKU has developed a very interesting and cost-effective force sensing technology based on the deflection of polymers and capacitive sensing. Again, I want to emphasize these neat sensors are his work and not really, I don't claim any credit for. But again, we're excited that we could enable his technology to be tested in a realistic surgical robotics context by exposing the tool interface to him. So you can see this is one of his prototypes, which is a wrist-mounted sensor, and it's shown up at the top two images. On the bottom left is the tool interface itself, where the tool snaps into the Raven based on our open mechanical interface, and then a power and CAN bus line going in to acquire the data. And that's one version of the sensor where the sensing is done at the wrist, and this other version has the sensing in the fingertips. If you look on the if you look where I just directed the pointer, you can see a sort of a V shape etched in the fingers, and that V shape contains the polymer film, whose deflection is sensed by capacitance. So it's, and they also have a commercial version in one of the commercialization of this type of sensor in one of the booths downstairs. So the way we evaluated this, so now suppose we want to sense force at the wrist and feed it back to the human operator. You have a very challenging, well, straightforward theoretical problem, which is rotating the sensed measurement from the wrist frame of the instrument over to the user's frame. And so how can you do, with access to every line of the source code, that's fairly straightforward. I want to keep on time, so I won't go into details of this experimental apparatus, but it's basically pulling on a rubber band, so we know the actual direction of the force vector as ground truth. And part of the other thing about the Raven is we've been working hard to improve, and of course we're never going to be done with documentation, but we're proud of the state it's in right now. So the kinematic analysis is an online technical report, and we're on version 2 of the entire inverse kinematics solution, which means this time we've picked the frames in exactly the most logical places and used the clearer notation. So now we have an inverse kinematics analysis we're quite proud of, and that's transparent. And using that, we implemented an interface to that sensor using our software stack. So what you see here is the standard software architecture that Raven is built on. The bottom layer is the standard Linux kernel recompiled with one configuration flag to do a patch set that allows hard real-time interrupts or dispatching, scheduling, so that our controller runs at a very deterministic 1,000 hertz control on top of the kernel. We also have, from the old teleoperation days, a very direct UDP-based interface for controlling it in a very fast teleoperation mode. But then we've successfully exposed a lot of interfaces to this through the ROS middleware layer, which we're using a lot, and we're finding makes interfaces to the system much more flexible. This next slide is a lot of somewhat superfluous detail and hypothetical things, so we won't spend too much time on it, but the central blue box and the node on top of it, right, Raven Control, is the key interfaces that we expose. So now, for this specific experiment, SKKU exposed a ROS node in their own computer here that was informed by the kinematic model and so in principle that's enough to rotate the sensing measurements into the user's frame, except you also have to know where the robot is. So Raven's nodes expose the joint angles, which now allow the transforms to be updated to drive force feedback in the haptic device. And those, all this interfacing was quite easy for us to put together in the few days that we had to do our integration. Another example was last year's meeting of DVRK, which is the Da Vinci Research Kit, which has very similar aims and has been good about cooperative activities between our two communities. And so at the last DVRK meeting, in an hour or so, the experts on both sides were able to hack together a link so that Simon DeMaio there is using the Da Vinci master hardware to teleoperate the Raven on the right. That's the picture I was talking over. Here's an example of how the ROS interface enables research results to be prototyped quickly. So Andrew Lewis, who's now with Applied Dexterity, did a nice master's thesis, and we wanted to leverage accelerometers to do gravity compensation because in the standard industrial robot, gravity compensation assumes a fixed gravity vector, but surgical robots are constantly being tipped and placed in different angles by the surgeon. So why not sense the gravity vector? And Andy thought about it hard and did a very nice refactoring of gravity compensation problem into a very economical argument or formulation. So using, if all we have to know is the center of mass of each link and its lumped mass in the local frame, then at each step you transform each center of mass into the current frame, add up all the torques for all those relative to the first joint, and project it onto the joint axis, and now you have the torque due to gravity. So that's a very fast computation, which is very economical in terms of parameter identification. You repeat that for each joint, and you can even factor the gravity vector out. So I'm running short on time, but the point is the accelerometer and a tiny computer exposed the accelerometry measurement on ROS and then networked it right into the robot's control system. And this is the experimental evaluation. The actual hardcore results of this were presented in ICRA last summer, this summer in Hong Kong. But there's the sensor on the base in the circle there, and by rocking the board back and forth, we could evaluate it under disturbances simulate situations like having the robot on a ship in wave motion and compensating that, again with a very quick set of dynamics. So I'm actually, my little dynamic speeding up has gotten me in under the wire, and I'll summarize with a few conclusions that we've aimed at exposing a lot of open interfaces at both the hardware and software level, and the goal is for all of us to stop reinventing the wheel and collaborate and exchange ideas. If you have a Raven, you already know what we're doing together. If you don't, but you have an idea, find a partner who has a Raven, because we could do something together. So thank you very much for your time, and I look forward to having questions at the coffee break, and we'll move on and stay on our very tight schedule.
Hi everyone, my name is Omid. I'm a PhD student from University of British Columbia. In this paper, we're exploring the applicability of a novel force feedback control framework for bimanual telerobotic surgery. The core idea of the control framework is that when completing two-handed tasks involving an action and a reaction force, like suture knot tying and palpation, the forces applied on the environment by the action hand are not transferred back to the same hand, but rather to the reaction hand using our proposed asymmetric control framework. Such a method provides an intuitive way of feeling the force while avoiding the instability issues with the traditional bilateral teleoperation controllers, since the control loop is not closed from the slave to the master of the same hand. Actually, the control loop is closed through the human operator's body that could isolate the action hand from the forces that are fed back to the fixed hand. The technique, in this paper, the technique was implemented on the Da Vinci surgical system using the Da Vinci Research Kit, or the DVRK, controllers that enable complete access to all control levels of the Da Vinci manipulators via custom mechatronics and open source software, which developed at Johns Hopkins University in collaboration with Intuitive Surgical. We integrated the DVRK controllers with a full Da Vinci Classic system in our lab at UBC, as you can see in this picture, and implemented the control framework on it. Using the DVRK controller with the Da Vinci Classic enabled us to conduct user studies in a reasonably realistic Da Vinci surgery environment where users can sit at the surgeon console and work under stereo vision while using our custom control algorithms. So to test the performance of our method, we conducted a series of suture knot tying and haptic exploration experiments in which a small group of users, both surgeons and novices, evaluated the system. The results showed that the proposed technique had some promise when implemented in a realistic system, but we're planning to do some further work to make the system fully usable. For example, for the suture knot tying, we compared the forces applied during 3 different scenarios, during in open case, robotic case, and robotic with haptic feedback phase. Yes. Please come talk to me during the interactive session if you're interested to know more details about how we implemented the system on the Da Vinci surgical system and the other results that I got from the studies. Thank you.
Hello everybody and welcome to my presentation with the title First 3D Printed Medical Robot for ENT Surgery. Disease or injury of the middle ear bones can lead to hearing problems or hearing loss. In this state of the art, the surgeon reconstructs the hearing bones using small prostheses. You can see down there in the picture. Herefore, precise maneuvers are required. The drawbacks are the limited accuracy and an unergonomic posture of the surgeon. The limited accuracy is due to the hand tremor of the surgeon, which is from around 1 millimeter to 0.1 for a trained surgeon. This can lead to revision surgery or to irreparable hearing loss. In our research, in our lab, a telemanipulator was developed preliminary. It's made out of titanium and PEEK, and which you can see here on the right down. My goal was to develop a disposable robot by reducing the costs and reducing the assembly time. I wanted to use the selective laser sintering methods of biocompatible polyamide. And the mechanical structure of the robot should be printed in one part. The size and the workspace should be the same like the previously micromanipulator. The idea was to replace the linear kinematics by a flexure hinge mechanism. We call it drag chain. And the whole mechanism you can see on the right side, the white thing is printed out of one part, and you afterwards have to clip in the motors, and down there you see the final robot with a surgical perforator. And the printed part, the printed structure, costs around $75, for example, at Shapeways. We made a preliminary experiment, and we asked, is the accuracy sufficient to contact holes with a diameter of around 0.5 millimeters? The result was that 85% of the holes were contacted successfully, and 95% of the holes were contacted inside the valid force range. Here you can see a small demonstration of the robot. My name is Konrad Insfellner. I thank you for the attention and see you later on the interactive session.
Hello, I'm Josh Peterson from Imperial College London, and I'm here to present our work entitled Mass and Inertia Optimization for Natural Motion in Hands-on Robotic Surgery. So hands-on robotic surgery is where the surgical tool is mounted at the end effector of the robot, and the surgeon moves the tool by directly applying forces and torques to the end effector. So this has several advantages. The surgeon remains in control of the procedure while still taking advantage of the robot's higher precision and accuracy. If you're using an impedance-controlled device, you can directly feel the forces of the tissue interaction through the tool, and other stuff such as active constraints and virtual fixtures can be applied to protect the patient. However, one of the disadvantages is that the surgeon is now additionally interacting with the dynamics of the robot, and this can limit the ability of the surgeon to maneuver the tool. So natural motion aims to improve that feeling, the feeling of the interaction between the surgeon and the robot, eventually towards the idealized case of operating with the tool without the robot attached. So there are many factors in the interaction going on, and so here we focused on the effect of mass and inertia that the surgeon interacts with at the tool point in redundant robots. So this mass at the end effector has been shown before to be a belted ellipsoid. So when you basically apply a force or torque in a particular direction, there's an effective mass that you feel, that you react to. And this ellipsoid is a function of the configuration of the robot and of the redundant degrees of freedom. So we've developed a method which optimizes the volume of this ellipsoid, minimizes it so that whatever the surgeon is interacting with is as small as possible, while we project this into the null space of the end effector so that we don't affect what the surgeon is doing. So in this way, we try to make it closer to what the tool is unattached to the robot without affecting what the surgeon is doing in terms of position and also when not force scaling. So to show this, we did some simulation results demonstrating that there's an effect over the workspace of the robot we were testing on, and also demonstrating that there's not a huge effect when you have a small amount of parameter uncertainty, which is common in typical systems. We also did some trajectory-based trials to demonstrate the effectiveness when compared to standard ways of resolving redundancy in hands-on robotic surgery. And so if you'd like to learn more and see our more current results, which involve implementing this on an experimental system, come see me at the poster session. Thanks.
Hello, everyone. My name is Ben Conrad, and I'd like to share with you some results my advisor, Mike Zinn, and I have found in a robotic catheter. In this animation, you see a catheter operating in the heart to treat atrial fibrillation. And generally, this catheter needs to make precision contacts around each of these vein openings, and then the burnt tissue forms a conduction block, which prevents errant signal from improperly activating heart muscle. As the energy delivered is a function of the contact force and contact duration, successful therapies require good force, position, and regulation. The desire for patient safety prefers catheters constructed from soft polymers, but this introduces nonlinearities which substantially impair force and position control and therefore decrease patient outcomes. So this is a problem that we're tackling by interleaving discrete rigid joints between successive flexible segments in the catheter. These linear joints have the first purpose of serving as linear compensators for the flexible segment errors. But depending on their design, they can also increase the control bandwidth and the overall dexterity of the manipulator. And so our goal here, our overall goal here, is to realize the performance of traditional manipulators in an inherently safe catheter system. So to look into this a bit further, we constructed a demonstration prototype which includes the core concepts of interleave manipulation. So all actuators lie outside of the patient, and this allows a wide access to high-performance servos and avoids the need for drive minimization or serialization. The motions of these drives are communicated through a flexible vasculature model to an interleave manipulator, which in this case would be inside the patient's heart. So the prototype, looking more closely, it has two flexible segments, a proximal segment which rolls, and then a distal segment which bends like a normal catheter. The distal segment is actuated by a tendon which is routed along the outer diameter of that yellow catheter, and such that when you actuate that tendon, it bends in an arc. The rigid joints consist of a pitch and a roll, the 3D printed parts. There we go. And these are remotely actuated by large distal reductions. We're placing these large reductions, 700 to 1, in the right inside that heart. That way you can minimize the effect of compliance due to that flexible drivetrain. So here's a video of the prototype in motion. What it is it's the task here is to target at a sinusoidally moving point, while the pitch joint moves from -80 to 30 degrees, and then you're trying to maintain a constant tip to target distance. Thank you.
Hello everyone, my name is Ehsan. I'm working with Professor Miloš Zefran at the University of Illinois at Chicago. Today I'm presenting our work on estimating interaction force during minimally invasive surgery, MIS. When talking about MIS, the most famous robot that everyone has heard of is Da Vinci. It works in a master-slave mode, and as one of the speakers today morning mentioned, the keynote speaker, a very important shortcoming of this robot is lack of haptic feedback. So there are several ways around it. One way is to measure the torque and force in each joint of the robot arm. This is the way that DLR implemented this in their IROS robotics system, and then they feed back the result to the forces to the surgeon through these haptic interfaces. But it's not a good solution when we want to have a force feedback from the tooltip. And you can see that with these tools, we cannot install any sensors at the tooltip. So what should we do? There's another approach, which is estimating the force. And one way to estimate the force is from the endoscopic image. If we have a stereo vision endoscopic image, we have two cameras, and we can build up the 3D model of the organ, find the deformation model, and then based on the deformation model, we can estimate the amount of the applied force by the surgeon. So again, according to another speaker here, in IROS, we need to adjust our solutions to the clinician's needs. So what is the need here? They want to use their own existing devices. They don't want to add hardware or update their systems. Most of them are using the monocular endoscopes, which means that there's only one camera. So the stereo vision solution is not working here anymore. Our proposed method is to use a picture from monocular endoscope, fit a virtual template to the image. I will explain this in my interactive session in detail, what is this virtual template, then applying this algorithm deformation reconstruction to this virtual template, and this is the result that you can see. The deformation is almost matching the actual deformation, and then we can use one of the existing equation works for estimating the force on this virtual template to calculate to estimate the force. Thank you.
Hey, hi everybody. So for those of you who haven't been up here, the thing that tells us how much time we have left looks exactly like a bomb that's got 3 minutes left on it, on my counter. So sorry, no more jokes, I got 3 minutes. So my name is Troy Adebar. I'm presenting work that was done with my advisor, Alison Okamura at Stanford University. And the title of our paper is Recursive Estimation of Needle Pose for Control of 3D Ultrasound-Guided Robotic Needle Steering. So this work is on robotic needle steering, which is a technique that uses a robotic system to control flexible metal needles with asymmetric tips along controlled, curved, three-dimensional paths through tissue. So our approach to this leverages the fact that if you have a flexible needle with an asymmetric tip, the net lateral force that acts on the needle as you insert it into tissue causes it to follow a roughly circular path. So to date, this effect has primarily been validated in artificial tissues like PVC rubber and gelatin, but our current project focus is on image-guided needle steering in more realistic models like animal cadavers and ex vivo tissue samples. So overall, our project goal is to combine kinematic models of needle steering with real-time three-dimensional ultrasound imaging in order to place the tip of a steerable needle at a target in the body as accurately as possible. So as we start to look at more realistic tissue models, there are two main types of noise that we have to start to deal with. So one of them we describe as process noise, and by this we mean the fact that in realistic tissues, inhomogeneities like small blood vessels and fascia, as well as motion of the tissue that's caused by respiration and circulation, they both cause the needle tip to deviate from the ideal kinematic path that we have in our models. We also have measurement noise, and by this we mean the fact that really just the medical imaging we use to get the pose of the needle tip is pretty poor quality. So it turns out that when you have these very thin curved needles in B-mode ultrasound, which is the standard type of ultrasound you see in the bottom left there, they really are difficult to segment automatically, partially because they're either not visible or partially because they just look a lot like other structures in the image. So we've described using techniques where you vibrate the needle and image it using Doppler ultrasound, which is what you see in the right there. And it makes it easier to do an automatic segmentation, but the results are still very noisy, especially when you're talking about orientation of the needle tip. So in this work, we describe an approach that deals with both types of uncertainty in the measurement and in our model, using a recursive estimation scheme that's based on an unscented Kalman filter. So this relies on a characterization of both types of noise, which we describe experimentally in the paper. And as a result, we're able to use medical image segmentation results for direct feedback control, which otherwise wouldn't be possible because they're just too noisy. So using this unscented Kalman filter scheme, we get a 76% reduction in overall placement of the error, or the placement of the needle tip, and we're able to do it with an average error of about 2 millimeters, which is about the same as a human can do with medical image guidance. So I hope you'll come see me at the interactive session. Thank you.
Hello, my name is Hyungyul Choi. This work is done by one of my PhD students, Dong-hyuk Lee. Actually, most of the overview has given by the keynote speech from Blake Hanna for this. I will give some detailed introduction of my sensor system. So I don't want to repeat the research objective and background of my sensing system. Actually, the force information is very much necessary in the surgical robots. Okay, in summary, there exists several force sensing schemes. In overall, we have 4. So one is on the wrist, and then the other one is a grasp integrated, and then at the shaft, and then at the actuation unit. But according to our review, then we can say that most feasible solution is on the wrist and the grasp integrated approach. So we carry on the research on both of this, and then in this paper, I will introduce the sensing system on the wrist, and then the other will be presented to one of my students in the next presentation. Okay, this is one basic idea. We integrated a very tiny and disposable multi-axis force sensor at the wrist, and also 2 tension sensor, which is used for measuring grasping forces. And then the grasping force and management forces will be computed by each sensor's reading. And the details of the sensing scheme will be explained in the interactive sessions. Okay, this is implemented once, so this is what completely mechanically adaptable to the Raven. As you can see, we have a 3-axis force sensor here, and then there is a grasping force sensor on the back. And then the diameter of the sensor is 10 millimeters. So we can sense 3 Cartesian forces, 1 grasping forces. Okay, this is a demo video. So we just put together the robot string, and then you can see that it's a sensitivity, and we can sense very sensitive forces by using this sensing system. And also, this is a demo for grasping forces. So according to the amount of grasping force to be given, you can see the change of grasping force magnitude. Okay, this is information for my paper. You can see in detail in my presentation in the interactive session. And then the below one is information from a companion paper that will be presented by one of my students in the next session. Thank you very much.
Good afternoon. My name is Tim Betua from Waseda University in Japan. Today I would like to present our work in estimation of needle tissue based on force patterns. Most of the research for percutaneous robots focus on the planning of the steering needle either in preoperative simulation or intraoperative steering needle. However, these methods have their advantages and disadvantages. And instead of choosing one or the other, we want to combine the strengths and the weaknesses of both to achieve a more accurate needle placement. For example, needle steering can compensate for errors in the simulation and patient's involuntary movements, but due to the limited maneuverability of the needle inside the tissue, you need to know in advance where the target is to calculate a path that can be followed by the needle. Furthermore, percutaneous robots must also adapt and react to unexpected events. So in this case, in the image on the right, we can see that the needle, instead of puncturing the tissue because of the presence of a ligament, is deforming it. For that reason, we proposed to include a situation awareness block in the control model, whose function is basically to understand what is the current situation during the needle insertion process and estimate what will be the outcome based on the actions that can be taken. In this case, we are focusing on the prediction part, and the idea is basically try to find common force patterns in the needle insertion force, so later on, given an initial force pattern, we can predict what will be the shape of the needle insertion force, and with that, simulate what will be the end position of the target. In this case, we're focusing on the two main components of the needle insertion force. Friction, which we see as a general trend, which is modeled as a linear model between the puncturing events and the cutting forces, which is fitted locally with a quadratic model to estimate the local value of the elastic modulus. This process is done recursively for each puncturing event, so then we can simulate the end position of the target. Looking at these two parameters together in Liber, we were able to identify four common patterns that allow us to understand what is the current situation between the needle and the tissue. Thank you very much, and I hope to see you later in the interactive section.
Good afternoon, everyone. My name is Eugyeom Kim. I am a PhD course student in Seonggyungan University, Korea. I will tell you about design and realization of the grasper integrated force sensor for minimally invasive robotic surgery. MIRS has provided significant advantages based on master-slave system. However, the lack of first information in the system caused tissue damage during robotic surgery. Therefore, the objective is the development of sensing system in the surgical robot for safe grasping and force feedback control. There are 4 possible locations of the sensing system. To get accurate force information, we have tried 2 sensing approaches on the wrist and the grasper in the surgical tool. Therefore, two kinds of sensing systems were developed. In this research, a grasper integrated force sensor is introduced as shown in right figure. Basically, the forcep, including two graspers, measures force data by four capacitive sensing cells integrated to the grasper. Depending on the data, the cell, depending on the data, contact forces are directly measured on the grasper, such as normal and shear forces. And the forces can be transformed as three axial pulling and grasping forces. The calculation of the forces is conducted by 4x4 transformation matrix. For the realization of the sensor, it consists of triangular prism structure, flexible PCB, and base frame. Actual assembled grasper integrated force sensor is shown in right figure. It is a demonstration. After grasping the tissue, X and Y axial pulling motion show grasping X and Y axis data changes. And after grasping, G axial pulling motion also represent grasping and G axial data changes. If you have any question, we can discuss this research in upcoming interactive section. Thank you for attention.
Okay, good afternoon, everybody. I'm Guillaume Morel from the University Pierre and Marie Curie in France. This paper is about the robotization of confocal endomicroscopy. So it's a new imaging technique that consists of applying a probe, which is 2 millimeters in diameter, in contact to tissues. And the probe, thanks to an optical fiber, provides real-time microscopy of the tissue surface. So when you can stabilize that on a tissue like this, you get the image on the bottom, which is an image of a micro vessel where you can see the red cells moving. So 1 pixel is 1 micron on these images, which is a resolution that is enough to perform pathological analysis. Unfortunately, pathologists also want to have wide range images. And to do this, a solution is to sweep the probe over the surface in such a way that you can glue together the successive images and build a mosaic thanks to a small motion of the probe. So that's the context of the paper, and the paper more particularly deals with the problem of tissue deformation. So back to the lab here with a very high precision robot, we can apply precise trajectories to the probe and then build mosaics like this one. And you can see that there is a large discrepancy between the motion of the robot, which is the red circle, and the mosaic, the relative motion with respect to the tissue. And all of this is due to the fact that you have tissue deformations due to friction. In the paper, we developed a model to describe this interaction problem between the probe and the tissue. So the model is extremely simple, as it consists simply of column friction plus localized stiffness. And it ended up in a very simple model for the deformation that has only one parameter initially, which is a loading distance. In spite of its simplicity, it describes quite well the behavior of the deformation, except that for these plots that are compared to experiments, we had to include anisotropy, which I will detail in my presentation. In the interactive session, you will also have more material on how we compensate that deformation thanks to visual servoing, how we use it for planning the trajectory for building a mosaic thanks to that model, and also some mechatronic instruments that can move the system and use the visual servoing. So thank you for your attention.
Good afternoon. My name is Haipin Chen from Texas State University. So as we know, there are many complex assembly processes in automotive manufacturing. So here, I'll give you an example about this torque converter assembly processes. So in this process, there are many process-related parameters have to be optimized in order to minimize the cycle time and maximize the success rate. Okay, in this research, we proposed an online method to model this complex assembly process to maximize the success rate and also to minimize the cycle time using a support vector regression method. So I will show you a video recording this process here. Okay, so I will not go through all the detailed methodology, but here give you the assembly process performed in the robotics lab at Texas State University. So you can see there are many parameters. You can see this rotation angle and the rotation speed, and also this we call this hopping frequency. So in this process, there are more than 20 parameters to be optimized. So the issue is how can we model this process? Because this is very challenging. We could have using different robots and different assembly processes and also for different part variations. So in this case, by changing the parameters, you can see now the hopping speed is changed. So by changing the parameters, we construct the model iteratively, and also based on this constructed model, we optimize, we predict what's the optimal process parameters. So then based on this prediction, we perform the experiments again. So then based on this iterative process, we can optimize the process parameters. So now you can see we can use these parameters to do the experiments again. So in case if there are some failure data, because in our assembly lines, there are a lot of failure data, we can still use the failure data to optimize, to construct the model. And also if there are some short cycle time, we will not consider it. So after a certain number of experiments, we can find an optimal parameters. So in this way, for this complex process, so normally we found the parameters in about 10 to 15 experiments. So after we found the optimal parameters, so we perform the experiments to verify if the parameters is optimal. So now we can see this, we use this optimal set of parameters to perform this experiment again. So we have been tested this methodology at the Ford Motor Company. So the test was very successful. So now we are working with Ford Motor Company to commercialize this product. Okay, so now this is the testing. We can see we can change.
Hello everyone, I'm Ryosuke Murata from Kyoto University in Japan. Today, I'll talk about the new user interface system for mobile manipulator. These days, teleoperated mobile manipulators are required to do some manipulation tasks in such inaccessible environment for human, for example, an earthquake disaster area and so on. Now, our research is focused on this interface. Under such situation, we have some problems. For example, sometimes we cannot use real-time video stream because it's a low bandwidth environment due to a damaged or poor temporary wireless network infrastructure. Also, sometimes such environment has many confined spaces, so we should not add any unnecessary hardware for the task to the robot because we should make the robot size minimum as possible. So now, our purpose in this research is to make the teleoperation interface for mobile manipulator that is effective for manipulation task and available under such situation. So I'll explain about the research of teleoperation interface for mobile robots navigation task. It's called teleoperation system using past image record. When the robot is going like this, so this system stores images from the robot like this. So it's called past image record and renders 3D model the robot on one selected image from the past image record. So now this system can provide such third-person view image to the operator with no real-time video stream and no additional hardware. And also, it was proved to be a very good way to improve the operator's situation awareness. So based on this system, we proposed this teleoperation system using past image record for mobile manipulator. Actually, it uses this similar mechanism, but it has two big improvements from previous one to fit mobile manipulator. One is that we proposed image evaluation standards. Based on these standards, this system can provide and choose more suitable image for manipulation task. And second one is that we let the operator concentrate on only the end effector. I mean, this system shows only the end effector, I mean, not whole the robot. And operator can input only the end effector's movement. So now it's easy way to understand for you, I think. So now you can see a moving end effector on proposed view. So we did user experiment, and its result shows our system is more effective than other typical interface. So that's all. Thank you for listening. See you later.
Hello, my name is Hawkeye King. I'm a postdoc at Imperial College, but today I'm going to present work done with Professor Blake Hannaford at the University of Washington entitled Experimental Evaluation of Virtual Fixtures for Object Telemanipulation. Performing tasks telerobotically is difficult compared to performing them with the human hand. Some of that's due to mechanical difficulties, such as reduced degrees of freedom. Sometimes there's time delay, but there's a big factor of what I call operator deficiencies, that is poor proprioception and reduced visualization compared to direct vision. One mechanism that's been proposed to accommodate this is haptic virtual fixtures, that is force feedback, that can perform two functions that were identified by Abbott and Okamura, that is forbidden regions where you're prevented from entering regions that might cause damage, or guidance virtual fixtures that help guide you towards accomplishing a task. So I was interested in actually exploring how these affected object manipulation. So I developed this task roughly based on the fundamentals of laparoscopic surgery block transfer task. The user is required to pick up rings located on the right side of the board there and place them on pegs located on the left side of the board. To test how virtual fixtures impact performance on this task, I developed a forbidden region virtual fixture that kept the user outside of environmental contact except for the region where he or she intended to operate, and also a guidance virtual fixture that helped push the user towards the region of interest where they wanted to perform either the block pickup or the block put down action. These were implemented on the Raven 2 telesurgical system, and 22 subjects performed the task. They did 75 iterations of the task in each of 3 modes: guidance, forbidden region virtual fixtures, and an unassisted mode, and these were compared. Jumping right to the conclusions of the study, there were some benefits and some drawbacks. Benefits included improved safety with the forbidden region virtual fixtures and faster movements through sort of ballistic movement segments of a task. However, there were some detriments that led to some suggestions for future virtual fixture design. Specifically, it's important that virtual fixture geometry be based not only on the task that you're trying to accomplish, but on human factors, such as what the human sort of reaching workspace is and how humans normally perform manipulation tasks. And also, we just uncovered that it's important to perform a smooth transition between regions of the workspace where the fixture is operating and regions where it's not. And those smooth transitions will help the user sort of effectively move from one segment to the other. So I'm happy to discuss numerical results with you in interactive session number 14.
Hello, my name is Matthias Schreutz. This is trying to work with my students, Cody Canning and Tom Donahue. And it is about investigating human perceptions of robot capabilities in team tasks, remote team tasks, where the human sees only the video feed from the robot, but not the robot itself. This started out as a follow-up study to work that we've done in the past where a person needed to coordinate 2 different robots using a very simple interface. I'm not going to tell you the task details, they're not relevant here, but they had to basically switch between 2 videos, and they saw the video feed from the robot's camera in the environment. And you can see them up top and at the bottom. Those would be 2 different ones, and the robot, the subject had to instruct one or the other robots at any given point in time. And what we found was that when one of the robots assumed autonomy while the subject, or autonomous behavior towards the goal when the subject was busy with the other robot, then people did better in the task, it improved the objective task performance, and we wanted to replicate that study in the case where one of the robots was a real robot and not a simulated robot. So here's an example of the Pier 2 in an environment that we constructed. There's a bird's eye view of the environment in the upper left corner. And the subject would sit in front of a screen just with a prior experiment, look at the two video feeds. Here's a video feed from the real camera from the Pier 2 doing the task. Here's a video feed from the simulated robot in the environment. And we let the subjects run with both robots, not autonomous, one robot autonomous, the other robot autonomous. This is sort of the experimental procedure that you see at the bottom. And the expectation was that we would see an objective improvement of the task based on the robot's autonomy, and that we wouldn't see any effects based on the video feed between the real and the simulated video. Surprisingly, we didn't find any difference on objective measures, so autonomy didn't help. And even more surprisingly, we found a difference on the video feeds. The robots that were, we found the difference that real video feed robots were considered to be more collaborative and more capable teammates. And this is without having seen any robot. So we did another experiment where we thought, well, maybe we need to let people watch an interaction and not compare the two video streams, and maybe we need to prime them with a particular robot picture. So we showed them these pictures. We did an MTurk study. They watched the video of that kind of interaction. We didn't see any difference between any of these robots, no difference between real and live video. So what we figured then, maybe the subjects needed to interact with the robot, so we added an interaction control to the mechanical Turk study, and lo and behold, we did see a difference again. This time, they didn't have a comparison between real and simulated video, but the difference is much more complicated. And if you want to find out the details, then please see me at the session after. Thanks.
Good afternoon. My name is Geeta Sukhtankar from the University of Central Florida, and this is joint work with my former PhD student, Benny Lewis, who's now at Lockheed Martin. And today I'll be talking to you about user modeling of expert-novice differences in human-robot interaction. The purpose of our experiments was to find the best solutions for constructing an intelligent user interface for allowing users to command a multi-robot manipulation task. The multi-robot manipulation task was deliberately designed to be impossible for the robots to do autonomously and difficult for the users to do completely under teleoperation because it involves moving both robots concurrently. If you're interested in our research, please check out our low-cost robot design and the code for the software user interface, which we made publicly available. So in this task, we ask our human subjects to do the following. They're told that they need to clean the clutter from this environment by moving all the objects in the environment to the basket in the back corner of the room. The main catch is that some of the objects are bulky and cannot be moved by a single robot. So the robots must cooperate to move these large objects. So in this study, we looked at two classes of user interface paradigms. Configurable user interfaces in which the user is allowed to tune the user interface according to their specifications. We use a very simple learning from demonstration algorithm to allow the user to create programmable macros to automate difficult sections of the task. We also have an adaptive version of the user interface in which we use adjustable autonomy to selectively reduce the operator's workload. So the main contribution from this research is a user modeling approach for reliably predicting which group of users will perform well with a specific interface type, adaptive versus configurable. So this is the view from the user interface. The user looks on the environment with different camera views. The user is controlling the robots using a combination of Nintendo Wii remote commands, but we also have a Kinect pointed at the user, so we use gesture recognition to control the arm elevation. The user modeling aspect involves training a semi-supervised classifier from short teleoperation traces to predict the user's expertise at different aspects of the task. The features involve backward, right, left robot movements, things essentially extracted from a histogram of the user's commands. So you'll have to come to the interactive session to find out more about the results. But the interaction effect was very significant. Experts performed better with the configurable interface and novices with the adaptive one. So we've made the code freely available. Please come to the session. Thank you.
So hi everyone, I'm Ben, and I'm working with John Anders and Professor Bernie Medler at the University of Minnesota. So our topic is modeling visual motor control and guidance functions in remote control operations. The motivation of the research is to investigate the interactions between human perception and teleoperated vehicles and environment and task elements. This can be described as a multi-loop hierarchical structure. So in our research, we'll try to answer two questions. The first question is what information is required for human pilot to deal with different control modalities? And the other question is how this information is extracted. So here is our lab. We hire human pilot to wear eye tracking glasses and to control a micro helicopter. So here is a short video showing the experiment. So we perform different tasks in this environment, and with eye tracking glasses, we can capture the gaze movement and decompose them into different modes like saccade, smooth pursuit, and fixations. And then we can couple in this gaze mode to human control actions. And here we can then integrate the data of gaze and helicopter for analysis. So here, the red line shows the helicopter trajectory, and the straight lines with blue star shows the saccades. It indicates that the functionality of saccades is to measure the gap between the current states and their goal position. And here shows the velocity of the helicopter and the gaze under smooth pursuit mode. We can see that we can from the result we can get that the functionality of smooth pursuit is to measure the position and velocity of the helicopter. So with this information, we can construct a block diagram of the human interaction model. So here in this paper, we try to do two things. The first thing is to classify different gaze modes, like saccades and smooth pursuit. And the second thing is to relate this gaze mode to different functionalities, like goal estimation and helicopter state estimation. And I would like to talk with you more about this in our interactive session. Thank you.
Good afternoon, everybody. My name is Eric Rodriguez Serra. I work at the U.S. Naval Academy. And the title of my presentation is Transparency Compensation for Bilateral Teleoperators with Time-Variant Delays. In this talk, I want to talk about bilateral teleoperators that have time-variant communication delays, but where the slave robot has to go from a free motion environment where it's free to move to an obstructed environment where it has to make contact with a hard surface. Applications for this include manipulation, coding, writing, and even navigation. One of the main issues that we have with bilateral teleoperation with time-variant delays is that we typically tune our system for one of the environments, or we do a trade-off between both environments. That is, we may end up with a system that feels sluggish in free motion, and one that feels soft to the human operator when it makes contact with a hard surface. In this video, for example, the human operator is able to still manipulate the master robot even though the position of the slave robot is being locked by the wall. So basically, the human operator loses the notion of where that wall might be located. Our control objective is to correct for that position error, sometimes called position drift, and to transmit a higher impedance to the human operator whenever it makes contacts with a wall, and to transmit a low impedance when the slave robot is free to move. Our control approach is based on the wave scattering transformation, but we also use an energy filter to accommodate for time variant delays and data losses. And the key aspect of our control approach is that we are using the wave impedance, a control parameter, to actually adjust the impedance being transmitted to the operator. Basically, we're going to increase the wave impedance whenever it makes contact with a wall, and we're going to decrease it. And that has to be a stable transition. These are some simulation results where we can show that the position error is reduced. And more importantly, this shows that the stiffness or the impedance being transmitted to the operator is improved when we use our control approach. We want to be in the upper left corner of that graph. Finally, I want to thank you for your attention, and I hope to see you at the interactive session. Thank you.
Good afternoon. My name is Christian Emmerich, and I'm from the Research Institute for Cognition and Robotics at the Bielefeld University in Germany. And I'm going to talk about model-free path planning for redundant robots using sparse data from kinesthetic teaching. So the vision behind our work is that humans and robots become co-workers, collaborating with each other efficiently, and therefore these robots need to be easily adaptable to changing environments or workflows. So there's a lot of progress that have been made in the recent years in developing such robots. We have compliant actuators, which are lightweight and have lots of degrees of freedom, and it seems very easy to teach and interact with these robots. However, when it comes to real-world scenarios, we often have to face the problem of acting in confined workspaces and cluttered environments, and especially for non-expert users, it actually seems not that easy to teach a robot a specific task. So the problem our approach wants to address is, given a robot placed in such a confined environment, how to enable non-expert users to teach these robots to move autonomously in this environment without having collisions with the environment. We don't use any explicit model of the robot or the environment, nor do we have any external perception, because often these are not available in industrial scenarios. In contrast, our approach is based purely on the data which is gathered through the very structured user interaction, during which the user explores only the relevant parts of the workspace. Based on this data, we learn a navigation graph of the free task space. We here use the instantaneous topological map algorithm, and we needed to enhance this with some bootstrapping heuristics to improve the connectivity. You can then plug in your favorite path planning algorithm to obtain a task-based trajectory from start to goal. And we combine this then with our previous work on learning from demonstration, or previous work on learning of redundancy resolutions with neural networks that enables us to transform the collision-free task-based trajectory into a collision-free joints-based trajectory, which then can be executed on the robot. This video shows how it's going to look like. It shows my colleague and former student Daniel Seidel, who did a lot of work in this project. And he's going to teach the robot according to this environment where we have two objects placed beside the robot. And already while he is interacting with the robot, the topological map of the free task space is constructed, and also the redundancy resolution is learned online. So if you're interested in our work and if you're interested in how this video is going to end, please visit me in the interactive session. Thank you.
Hi, my name is Andrei Haidu. I'm from the University of Bremen, and I will present you the work that I did together with my colleague Daniel Kolsdorf and my supervisor Michael Bates, learning task outcome prediction for robot control from interactive environments. The aim of this work is to help robots predict the outcome of their actions by learning from game-like environments. We have here our system overview. We illustrate in our first picture a user playing the cooking game, where he has the task to create a pancake by pouring a pancake mix over the pancake maker, and then with a spatula to flip the pancake. The interaction is done by tracking the user's hands and then mapping it on the simulated robotic hand in the game. During the simulation, all the physics data and the game events are logged, and eventually they are labeled with failure or success, depending if the user managed to complete his task. In order to learn the outcome prediction, we extract from the log data the position and the orientation of the simulated robotic hand, and we align it to a hidden Markov model from the states where the success and the failure events or outcomes are highly sparse. We can then learn detectors by learning a binary classifier on them for every state. This frame level failure detector then can be used for the robot while he's currently in an action to see if from this frame he will probably end up in a failed flip or pouring. And then he can replan its action. For the alignment, we use the 5-state hidden Markov model. We can see here from the second and the third state that the data are more sparse, and then we can train them for a binary classifier. With blue, we label the success rates, and with the red, the episodes with the failed events. Okay, here we have a failure detection example. We have the pouring represented with the yellow trajectory, which was successful, and then the flipping trajectory with blue, and then the red sphere, the failure is detected. This happens before the spatula touches, when it slides under the pancake. So the robot still has a chance to replan its action. Okay. Thank you for your attention.